Hello dear students, myself Mohammad Wasim, Assistant Professor in Mathematics, Art Science Commerce College Bandha. In yesterday's lecture, we have seen about the Laplace transform and we have seen the definition of Laplace transform of some basic functions, and we have seen some theorems which are dependent on Laplace transform. Now, since we have completed our first chapter, Laplace transform, we are going to start our new chapter, that is inverse Laplace transform. Inverse Laplace transform. Since we know that whenever we come across very complicated differential equation, when we solve some physical examples of nature, we come across some differential equation, or we can say complex differential equation. Then to simplify this equation, we use Laplace transform and convert this differential equation into algebraic equation. And we know that we have many methods to solve algebraic equation. So after using that methods, we get the solution of this algebraic equation after using many methods, and we get solution in algebraic form. So we again convert with the help of inverse Laplace transform into the problem form. We convert the solution into solution of the form of question given by using inverse Laplace transform. So, study of Laplace transform and inverse Laplace transform both are very important to solve complex differential equations. Now, we have seen how to use Laplace transform in previous lectures, in which we have seen some basic definitions and Laplace transform of some basic function, in which we have seen some theorems which are very important to solve differential equation, or we have to we use to convert differential equation to algebraic form. Now we have come across to this form, algebraic equation. We have converted differential equation into algebraic form. Now we know that we can easily solve algebraic equation by using many methods. We have solution of this algebraic equation. Now I want to convert this solution into a solution of directly a differential equation. Now we will learn about inverse Laplace transform, and before going to start, I want to show which type of notations and which type of symbols we are going to use in future. So, first of all, the definition. If Laplace transform of f of t is equals to f of s, means we have f of t as a function and we are taking Laplace transform of this function, we get the solution form in f of capital F of s, which is Laplace transform of this f of t. Then inverse Laplace transform. Then inverse Laplace transform is denoted by L inverse L raised to minus 1 f of s is equals to f of t. Correct? Inverse Laplace transform is defined as if Laplace transform of f of t is equals to f of s, then inverse Laplace transform is let L inverse f of s is equals to f of t. And as we know that in first chapter we have seen the definition, and just after that we have seen Laplace transform of some basic function. Similarly, we will go to inverse Laplace transform. Inverse Laplace transform of some basic function. Inverse Laplace transform of some basic function. Here function f of t is given. Now Laplace transform of f of t, that is f of s, and Laplace inverse of f of s is in third problem. First example. Laplace transform function is given as 1, and Laplace transform of 1, Laplace transform of 1 is 1 upon s, is f of s, and inverse Laplace transform of 1 upon s becomes 1. Correct? Actually, we have given the solution of Laplace transform. We have to find the problem. In inverse Laplace transform, we have already given the solution of particular function, and we have to use or we have to apply inverse Laplace transform to guess what is the problem there. So, if we calculate Laplace transform of 1, we will get 1 upon s, and if we take inverse Laplace transform of 1 upon s, we will get 1. Similarly, we have seen t raised to n, and the Laplace transform of t raised to n becomes n factorial s raised to n plus 1 whenever n is integer. Correct? So, here inverse Laplace transform of n factorial upon s raised to n plus 1 is t square. But whenever we want to solve such type of example, numerator, many times numerator is 1, so we can write it as inverse Laplace transform of 1 upon s raised to n plus 1 is equals to t raised to n and actual formula for inverse Laplace transform of 1 upon s raised to n plus 1 is equals to t raised to n upon n factorial. We just shift this constant number to right hand side, and we will get the inverse Laplace transform of 1 upon s raised to n plus 1 is equals to t raised to n upon n factorial. Similarly, we have seen Laplace transform of e raised to t, and it is 1 upon s minus a. So we can write it as whenever we find Laplace transform of inverse Laplace transform of 1 upon s minus a, we will get e raised to minus e raised to a. Similarly, for sin 80, we will get a upon s square plus a square, and if you want to find the inverse Laplace transform, since a is constant, many times this a is not given in example, so we will try to find without that a, so we will get inverse Laplace transform of 1 upon s square plus a square is equal to 1 upon a sin a. Correct? We will get 1 upon a sin a. Similarly, we can find cos a. So s upon s square plus a square, and inverse Laplace transform of s upon s square plus a square will become cos a. Since in numerator we have s, and to calculate inverse Laplace transform of such function will give us cos a if in numerator s is there. Now we have seen five basic functions, and if you accept this column, if you find inverse Laplace transform of 1 upon s, you will get 1. Inverse Laplace transform of 1 upon s raised to n plus 1 will become c raised to n upon n factorial. And if you find inverse Laplace transform of 1 upon s minus a, we will get e raised to at. And inverse Laplace transform of 1 upon s square plus a square becomes 1 upon a sin 80. Similarly, if you find inverse Laplace transform of s upon s square plus a square, will give us cos a t. And similarly, we can calculate we have f of t, f of s is equal to a upon s square minus a square. F of s is equal to s upon s square minus a square. F of s is equal to a upon s minus b square a square. F of s is equal to s minus b square a square. These four more basic functions we have to introduce in inverse Laplace transform. So f of s means Laplace transform of one function is given as a upon s square minus a square. We have to find that function. So using Laplace inverse Laplace transform of this, we will get, since we have h square minus a square in denominator, means it shows that it is hyperbolic sine, so we can write it as sine HAT. Inverse Laplace transform of a upon s square minus a square becomes hyperbolic sine 80, and many times in numerator we will get only 1, such as 1 upon s square minus a square. So inverse Laplace transform of this function is 1 upon a sine hyperbolic sine a t. Correct? Similarly, we can calculate the inverse Laplace transform of s upon s square minus a square, and it becomes cos a t, hyperbolic cos a t. Here we can see inverse Laplace transform of a upon s minus b square plus a square will give us e raised to bt into sine a. Similarly, this one, inverse Laplace transform of s minus b upon s minus b square plus a square will give us e raised to bt cos a. It is some basic examples which we are going to use in next lecture. So we will continue the further lecture. We will start our new examples in next lecture. Before we will start our examples, we have to learn all these formulas for next lecture. Please try to understand all the formula which are given in this system in this lecture, and try to write and try to learn this example. Till then, thank you. Bye.